Welcome to Pavinar's webinars for the pavement community. My name is Andrew Bram, and today we'll be talking about asphalt emulsion, stabilized unbound material, specifically with base and subbase material. To start with, we'll start with a very general background of unbound material in the pavement structure. We'll ask the question, why do we need stabilization, and list some of the benefits and pros to stabilizing in-place material. And then we'll go over a very brief Asphalt Emulsion 101, since this presentation is focused on asphalt emulsion stabilized unbound material. We'll then dig into the unbound treatments, so both the base and the subbase stabilization, and then we'll also cover the soil, also known as the subgrade stabilization. We'll talk a little bit about full depth reclamation, and full depth reclamation, or FDR, does use some bound material, but it also reclaims the unbound portion. So we'll talk about the mix design, the structural design, and some construction techniques. And then finally, we'll go over some additional resources. We'll go over an LRRB report. We'll go over the BARM, or the Basic Asphalt Recycling Manual. And then finally, we'll finish up with just a little overview of a website that I enjoy called roadresource.org. So let's take a look at some typical pavement structures. So all pavement structures have a surface layer, and this is bound material, anywhere from 3 to 12 inches. And for rigid pavements, as you can see on the right, there's typically one lift of concrete, and that's the very top layer. And flexible material often has multiple lifts. So you can see two lifts there of bound material in the flexible pavement structure on top. The base course, this is a select unbound material, and it's anywhere from 4 to 12 inches. This is usually only placed on flexible pavements. And then you have the subbase course, which is select or in place and modified material, also 4 to 12 inches. So it can be a select material, usually a little lower quality than base course, or it can be a modification of in-place material, and that's 4 to 12 inches. And then the subgrade, which is at the very bottom of each pavement structure, that is the in-place material. And the schematics are just general diagrams, but you can use one or more of each layer, and sometimes you can even combine the layers, as you can see here. So on the left, it looks like we have some rigid pavement on top of some flexible pavement. And then on the right, we have some rigid pavement on top of what looks like a bituminous bound base course or subbase course, and then the subgrade that's in place. So a couple different options here for pavement structures in the field. Now for this presentation, we're going to focus on the base course, the subbase course, and the subgrade. So those are the three pavement layers that we're going to focus on in this webinar. So for flexible pavement specifically, when we talk about the base, the subbase, and the subgrade, the base is a compacted layer of granular material. It can be treated or untreated. There are relatively stringent requirements for strength, plasticity, and gradation of the base material, and it does generally provide structural support. Now we can compare this to the subbase, which is also a compacted layer of granular material. It can be either treated or untreated, but it usually has lower requirements than the base material for strength, plasticity, and gradation. And it's generally not needed if you have a high quality subgrade in your flexible pavement structure. And then the subgrade material is the in-place soil, and it may need to be compacted. So these are the three different unbound layers in a flexible pavement structure. All three of these are unbound: the base, the subbase, and the subgrade. And there's several useful AASHTO specifications that can help understand these materials. So AASHTO 145 is the classification of soils and soil aggregate mixtures. AASHTO M 146 is terms relating to subgrade and soil aggregate. And then finally, M147 is materials for subbase, base, and surface. So these are all nice specifications that can help us better understand all of the details behind the base, the subbase, and the subgrade in a flexible pavement structure. We're going to hone in on one of these AASHTO specifications, M145, and this is the classification. And for those of you familiar with AASHTO soil classification systems, you'll recognize the A-1 and the A-7. And there's a -2, a -3, all the way down to -7. And the A1 is a granular material, the A7 is a clay material, and then you have pretty much everything else in between. So what we do is we take a look at the group classification. That's the A1, the A2, all the way through the A7. And that's based on your sieve analysis and the characteristics of the fraction passing the 0.425 millimeter sieve, or number 40. And so you can see here for A1 material, we have an A1A and A1B. We have an A3 and A2-4. The sieve sizes are slowly getting smaller for the total passing. So as you go down these numbers, in general, the material is a smaller size, but you could see also the plasticity index is increasing and a cap on the liquid limit is introduced as we get down to the A-2-4. And then when we get all the way down, there's an A5 as well that's not shown here, but when we get all the way down to the A6s and the A7s, you can see that this is all passing or all has requirements on a number 200 sieve. There's a maximum for the liquid limit for an A6 and a minimum for an A7, and then there's also that minimum on the plasticity index. So you can see the requirements are getting more stringent. I do want to emphasize, however, that for the classification and for the discussion of in-place stabilization, the sieve analysis, the liquid limit, and the plasticity index are the three most important characteristics. And if you take a look at AASHTO M145, there's actually more rows, so there are more that goes into determining the group classification. But I just wanted to highlight the sieve analysis, the liquid limit, and the plasticity index. And then taking a step back and looking at what makes an excellent or good subgrade, those are the A1s, 2s, and 3s. And then the fairs and the poors are the A4s, 5s, 6s, and 7s. So A1 is considered the best type of subgrade. A7 is considered the worst, and it's kind of a spectrum as you go down through all the different soil classifications. Now, transitioning to rigid pavement structures usually only have a subbase and a subgrade for unbound material. So the subbase is one or more compacted layers of granular or stabilized material, and it provides a uniform, stable, permanent support. The point of a subbase in a rigid pavement structure is to increase the modulus of subgrade reaction, because as you increase that modulus of subgrade reaction, you can decrease the thickness of the pavement structure. You also want to minimize frost action damage. The subbase layer provides a additional support that protects the bound layer to frost action damage. You want to prevent the pumping of soils. This is especially true for jointed plain concrete pavement. The pavement on the right is actually a continuously reinforced concrete pavement, but certainly for the reinforced concrete pavements, you want to make sure you prevent pumping of soils up through each of the joints, and you want to have a good working platform when you're laying the bound material. And then finally, the subgrade, similar to a flexible pavement structure, it's any sort of in-place material and it may be compacted. So why is stabilization important? Well, you want to ensure the successful long-term performance of the pavement structure. And this is done by constructing these superior bases. So by stabilizing this in-place material, by stabilizing this unbound material, you're constructing a superior base, and you can enhance the subgrade, subbase, and base material. So if your in-place material, your subgrade material is of poor quality, stabilization can help that. And if your local aggregate for your subbase and your base material are not the quality that you need, again, stabilization can help that. Once you do stabilize that in-place material, you increase the stability of the underlying soils in the base, and this in turn increases the resistance to both traffic loads and environmental demands. And so you can thin the bound pavement structure, which is tends to be more expensive. So the asphalt concrete or the Portland cement concrete layers tend to be more expensive. So by stabilizing your base, subbase, and subgrade, you can decrease the thickness of those bound layers. It also helps control dust and moisture on a job site. There's a lot of heavy equipment moving around, and you have the opportunity to salvage old roads. So there's a lot of older roads that are maybe in poor condition, and stabilization can help bring those roads back to life. So what are the different methods that we can actually stabilize the roadway material? Well, there are three different general types of stabilization methods. The first includes some sort of pozzolanic or cementitious material, which includes Portland cement, fly ash, and kiln dust. This is often termed a semi-rigid pavement. It increases the strength, but it also increases the brittleness, which is an issue. But this is a presentation on asphalt emulsion stabilization. So I ask you to turn to NCHRP report 144. If you just Google that report number, it's a very nice report talking about Portland cement, fly ash, and kiln dust stabilization. And it also has some information on lime stabilization. Because lime stabilization, the primary reason we use lime is it modifies and neutralizes the clay in the existing soil. So if you have an existing soil that has a high level of clay, lime can be added to it in order to neutralize that clay so you don't get that swelling, that absorption of water that you see with clay materials. And it can be combined with Portland cement or fly ash as well. And we're going to focus on the asphalt emulsion, which actually is a part of a larger group called asphalt cement stabilization or bituminous stabilization. And this can be either a foam process or an emulsion process. This is often termed a flexible stabilization, and it increases both the strength and the flexibility, and it can be combined with cement, Portland cement, and fly ash as well. But as I mentioned, we're going to focus exclusively on this presentation on asphalt emulsion. So, asphalt emulsion stabilization overview. This is your asphalt 101 slide. It'll be very brief, but asphalt emulsion in short is asphalt binders that has been turned into drop form, and those drops are suspended in water. So you have drops of asphalt binder suspended in water, and these drops of asphalt binder stay in suspension with emulsifiers, which are certain kind of chemicals. And if you're interested in learning more about asphalt emulsions, the University of Arkansas does offer a certificate, Introduction to Asphalt Emulsions. It'll give you a very nice overview of all the details about asphalt emulsions. You can simply search asphalt emulsion UARK, and it'll pop up at the top of your search engine. The process of asphalt emulsion stabilization is you have your existing aggregate and you either mill or reclaim it, and then you mix that existing aggregate with water and asphalt emulsion. And that's what's happening inside the drum you can see in that right-hand picture. Between the two axles, there's that large drum, and that is mixing it's milling and reclaiming the existing aggregate, and it's mixing it with water and asphalt emulsion. The asphalt emulsion coalesces, which means the binder droplets join together, and then the asphalt emulsion coats the aggregate. And this forms a waterproofed, stabilized layer. And there are three general categories that we look at. The first asphalt emulsion stabilization category is the subbase or the base stabilization, and this is where you have your aggregate base layer, and it's often used in areas when you have low quality aggregate. We have soil stabilization, which is only the subgrade, it's only in-place material. And in general, emulsion is not recommended for clayey soils, which is often one of the most stabilized soil material. But it has been used and it can be used successfully with other material, and we'll talk about that a little more. And when we're looking at soil stabilization, often unconfined compressive strength is specified. So that's an additional test you may see required when we're talking about soil stabilization. And then the third is full depth reclamation, or FDR. And this is where you have both unbound and bound material, and you stabilize that together. So you have your soil, your subbase, and or your base. It can be one, two, or all three of those. And you have a very thin layer of bound material. And what the nice thing about full depth reclamation is if you have a road that has a lot of layer distresses that is not structurally adequate, instead of removing and replacing all that material, you can reclaim it with full depth reclamation, and this removes all the layer distresses and it increases your structural capacity. So it's a very nice treatment for certain roads. So that's just a brief background, and now we're going to get into the three base treatments, or the two base treatments that we talked about in a little more detail. So starting with base and sub-base stabilization. What are some similarities between base and sub-base stabilization? Remember, base material tends to be a little higher quality, have a little higher strength. Sub-base material tends to be a little lower quality, but they have a lot of similarities. They're both compacted layers of granular material. They both can be either treated or untreated. They both have requirements for strength, plasticity, and gradation, and they both can provide structural support. So these are all similarities between base and subbase. Now, some differences are that the base has more stringent requirements on strength, plasticity, and gradation than the subbase, and the subbase is optional with high quality subgrade. So this is just the concepts of base and subbase in particular, and now we can move forward on how they're actually stabilized. And we're going to spend a little bit of time talking about the overview of the stabilization process, pre-construction considerations, construction considerations, and then quality assurance as well. So an overview of base and subbase stabilization is you want to improve the load bearing properties of an engineered aggregate layer. So this is crushed aggregate that is shipped in and placed in a roadway structure. And the structural layer coefficient of base and subbase stabilized aggregate is anywhere between 0.15 and 0.30, and that is using the 1993 AASHTO pavement design layer coefficient technique. Stabilizing your base and stub base, it enhances drainage and it decreases your instability. So if you have an existing soil that's unstable, not stable, a base and a sub base stabilization can help that. And then it's commonly used with, so if you're stabilizing your base or your sub base, you commonly place on top either a chip seal, slurry seal, or microsurfacing, or you could put asphalt concrete overlays or concrete overlays on top of your base or sub base stabilized layer. And at the end of the day, this is especially useful in areas that have low quality local aggregate, because those low quality local aggregate don't provide the load bearing properties that you need from your base or your subbase. Now we're thinking about pre-construction considerations. This is often base and subbase stabilization is often used in either new construction or complete rehabilitation. It can be used in all types of streets and in all climates, so it's very versatile. There are specific stabilization techniques required for various in-place materials or materials that you're trying to stabilize, but you can use them in combination. And when you're talking about the mixed designs, there are several things that you need to consider, and that includes gradation, your plasticity index or PI, your sand equivalency or SE, your pH, your sulfates or SO4, moisture content, density, your strength, durability, and freeze thaw testing. And then finally, at the end of the day, once you do that mixed design and you pick your stabilizing agent and you have the optimal amount, you may get out in the field and realize you need to adjust it. So there's a lot of considerations that go on here. And you can see here, this is an example of one recommendation of which type of stabilization to select. So if you want to use asphalt emulsion, you should only use asphalt emulsion if the sand equivalency of the in-place material or the material that's being stabilized is greater than 30, and your plasticity index is less than 6, and your P200 is less than 20%. Foam asphalt, the plasticity index should be less than 10 and your P200 should be between 5 and 20. If you want to use a cementitious material, your plasticity index should be less than 20 and your sulfate should be less than 3,000 parts per million. And if you want to use lime, your plasticity index can be larger than 20, your P200s can be larger than 25, and your sulfates should also be less than 3,000 parts per million. So you can see here I said before that asphalt emulsion should not always be used for all types of in-place material or base or sub-base material, and this shows why. There are recommended ranges of optimal performance for all these material. And there are various guidelines available. I encourage you to take a look at their website, roadresource.org, and look under the base and sub-base treatments. There's a lot of guidelines available there that provide more details behind these bullet points. When we're talking about the construction of base and sub-base stabilized materials, you want the weather to be above 45 degrees Celsius for asphalt emulsion, and you do not want any freezing within 7 days. You want that asphalt emulsion to fully break before freezing occurs. For equipment, you want to have a reclaimer, a distributor, a motor grader, which you can see on the right. You need various trucks to haul the emulsion in the water, and you need compaction equipment. It is important that all of this equipment is calibrated, especially when you're adding material or pumping material. If the equipment's not calibrated, you're not going to put the amount of material in that you think you are, and it will not perform as designed. So the sequence of construction is, if you're going to apply cement, you usually apply that dry on top of everything. Then you put a reclaimer or a mixer in, and you add your asphalt emulsion and water. You compact and you shape it with the motor grader, and then you allow it to cure, and after it's fully cured, you apply the surface course. Now, all of this can also be done at a central plant with asphalt emulsion. So if you have some base or sub-base, you can actually put it through either a drum or a pug mill at an asphalt concrete plant, mix it with the asphalt emulsion, and then deliver it to the job site and place it. So kind of following more the construction techniques of hot mix asphalt, but without any heat, and using asphalt emulsion instead of asphalt binder, you can also perform base and sub-base stabilization at a central plant location. Now finally, quality assurance is very important. You want to make sure that you're inspecting all steps, which includes the mix design, your surface preparation, the weather conditions, your traffic control, the equipment, like I said, calibration on the previous slide, workmanship. You can have the best materials, the best design in the world, but poor workmanship will sink any project. You want to make sure all the materials and water are being applied at the proper rate, and you want to make sure the material is fully cured before you put a surface course on, because you could have problems. And so different types of testing that you can do for pre-construction, that includes taking a look at the existing pavement structure. You can also use a ground penetrating radar for this. The layer thicknesses by taking cores. You want to make sure you're testing stockpiles that you're using, and you're sampling in-place material on the job site itself. During construction, you might want to run a sieve test on the reclaimed material to make sure it's within specification. You want to make sure all the temperatures are correct of all the materials that you're adding, the ambient temperature as well. Checking the injection rate of the asphalt emulsion and water, the application rate of the cement. Looking at the aggregate gradation, any physical properties and moisture content is very important. And then it's always recommended to place a test strip. So this is where you purposely only go about 500 feet to make sure everything is being done okay. You check all of the in-place material results. You may run a couple of tests, and then if everything is within limits, you can then continue on with the job, knowing that all of the equipment's calibrated and it's being constructed correctly. Once you've compacted your material, you may want to check the compaction density. You may want to establish a roller pattern as you go on. And then finally, the moisture content as the material cures is important. And when we think about acceptance criteria for agencies, you want to make sure at a minimum you are hitting your mix gradation. So if you take a sample afterwards, you want to make sure that gradation is appropriate, and you're hitting the correct asphalt emulsion and Portland cement content. So those are the three key things for acceptance from an agency perspective. Now thinking about the subgrade stabilization, there's kind of a lot of similarities here to the base and the sub-base. So we'll go over some concepts here for the subgrade. This is often used with new construction or rehabilitation. The goals is to either dry the existing in-place soil to improve the workability, to reduce the plasticity index, or to reduce the shrink and swell potential. As we mentioned before, asphalt emulsion is not recommended for clay soils. It generally is only used for non-cohesive soils. And as I mentioned, there's very similar pre-construction, construction, quality assurance considerations as the base and the subbase. And I want to point out another very nice document from UT El Paso, UTEP. It includes the design, construction of cement treated materials. So this goes through a lot of that subgrade stabilization concepts that we talked about that are similar to the base and the subbase. But if you Google FHWA / Texas 21 / 06949-1, just jot that number down. And if you Google that, it'll be one of the first things that pops up, and you can download the PDF. So now that we've taken a look at the unbound materials, let's transition to full depth reclamation, which is a combination of bound and unbound materials. So you can see here on this image, as the full depth reclamation reclaimer goes through your pavement structure, you're milling both granular material, and that can include base, subbase, and subgrade material. And then you're also including the distressed pavement. And this is the key difference. Full depth reclamation is a combination of bound and unbound material. Now it does increase strength, durability, and resistance to moisture damage. And there are 4 categories of stabilizing agents, and you need to choose the best for the in-place material. So this is very similar to the base and the subbase discussion for stabilization. The first is you can just simply do mechanical stabilization. And this is where the particles themselves interlock and you don't actually add any sort of additives. So that's one form of FDR. You can perform a chemical stabilization, which is cement, lime, or fly ash. You can do bituminous, which is asphalt emulsion or asphalt foam. And then finally, you can do a combination of the above. So there's various different treatments. Like the base and the subbase, there is a requirement to use the bituminous stabilization. You want that sand equivalency greater than 30, or the plasticity index less than 6, and you want less than 20% P200. You certainly should perform a mix design with FDR because these tend to be a little thicker than the base or the stabilized base layers. But unfortunately, there's no single current accepted mix design method for asphalt emulsion stabilized FDR. However, there are best practices to follow, and these are the individual components of the mix design. You want to obtain samples, both the bound and the unbound material, to the depth that you're planning on reclaiming. You want to crush the bound material to generate the reclaimed asphalt pavement, which kind of simulates what happens when the reclaimer chews up that bound material. You want to combine all of this material to desired proportions. So if you're reclaiming 8 inches and you have 4 inches of bound material, you want to include 4 inches of bound material 50% and 4 inches of unbound material 50%. So 50% of the bound and unbound material in all of your work. And you want to determine the combined gradation of that bound and unbound material, the plasticity index and the sand equivalent limit. You want to determine the maximum dry density and the optimal moisture content, and that can be done with a proctor or a modified proctor. And then you want to perform tests on the mixture of components. So you mix and compact at the optimal moisture content, and you add multiple percentages of asphalt emulsion. So it can be 3, 4, 5, or 6%, 4 or 5, 6 or 7%. It kind of depends on that in-place material. The finer material, the more asphalt emulsion you need. You want to cure the samples at 104 degrees Fahrenheit, usually for 72 hours, and allow them to cure overnight. So you want them to cool overnight. So this curing is very important, and this is specific for asphalt emulsion because you want to make sure all that water leaves the system. So for curing at 104 degrees Fahrenheit for 72 hours, that means those compacted samples will not have any water in them. And then you want them to cool overnight because when you run the tests, you want them to run at ambient temperature, which is the temperature in the field. You don't want them to run at an elevated temperature. So when you're testing for strength and durability, you want to make sure those are at ambient lab temperature, which is about 25 degrees Celsius or 77 degrees Fahrenheit. And the traditional tests to run are the indirect tensile strength or ITS. This is AASHTO T283. or the Marshall Stability Ratio, AASHTO T245. But you can certainly run other performance tests. In our lab, we've run dynamic modulus, low temperature cracking, the indirect tensile strength IDT low temperature test. So there are tons of tests that you can run. Pretty much any mixture test run on asphalt concrete, you can run on FDR as well. So similar to asphalt concrete, you find the optimal amount of asphalt emulsion to add based on maximum strength and durability, and you can then establish a job mix formula. So you have your optimal water content, your optimal emulsion content, and your optimal cement content. And as I mentioned earlier, this does all occur in the field, and you may actually need to make some field adjustments. But generally, if you're adjusting any more than 2% water or 0.5% emulsion, that means that there's a problem and you should not continue, because that means you're making major field adjustments. So if you make a field adjustment, you shouldn't add more than 2% difference in water, and you shouldn't add or subtract more than 0.5% emulsion, because that means you're getting into either different material or there's a problem with the equipment. Something's probably going wrong where the mix design was not representative of what's actually happening in the field. Now, looking at the structural design of FDR, again, looking at the AASHTO structural layer coefficients, this is quite an interesting discussion that we can have here on just this one slide. You can see these two research projects used just emulsion, and they had a structural layer coefficient of 0.24 to 0.25. But then if you start adding lime kiln dust, or if you look at foam and cement, or cement and emulsion, or just cement, that number starts creeping up. But then you start looking at other combinations, and the number continues going up. So in 2002, we had a cement structural layer coefficient of 0.28. In 2011, we had a cement structural layer coefficient of 0.41. In 2011, we had a lime plus emulsion structural layer coefficient of 0.26, and in 2002 is 0.37. So you can see there is a lot of uncertainty of exactly where the structural layer coefficient of full depth reclamation is. So I'm just going to kind of leave it at that. This could be a presentation in itself, because there's a lot that goes into determining structural layer coefficients, but I do think it's worthwhile to show that there is a wide range of what typically accepted structural layer coefficients of full depth reclamation are. Now, to put this in context, if you look at RDOT, the Arkansas Department of Transportation, their structural layer coefficients for asphalt concrete are 0.36 to 0.44. So there should be some red flags when you see FDR structural layer coefficients being equal to asphalt concrete structural layer coefficients, because FDR is not asphalt concrete. FDR is a semi-bound material. Asphalt concrete is a fully bound material. So you kind of have to question those higher ones. And then if you look at RDOT, they use a 0.2 for a cement stabilized base, which is quite a bit lower than any of these numbers. And there's a couple reasons for that. One, agencies tend to be a little more conservative. And two, this was based on a number that was obtained through testing by RDOT, so this is what they felt most comfortable with. Unbound material is 0.11 to 0.14, and then you can see here lime treated soil is 0.07. So kind of a key takeaway is that these stabilizing additives for research and the associated structural layer coefficients are also highly dependent on what was the material that was used in the FDR, because if it had a lot of poor quality soil, well, then perhaps that includes those lower numbers shown in the structural layer coefficient, because the lime treated soil you can see is by far the lowest structural layer coefficient. So there's a lot of different things going on in this slide. Certainly worth the discussion and worth recognition, but I just kind of wanted to bring this information forward so people would be aware. Now, pivoting to FDR structural design using Pavement ME, which is the mechanistic empirical method, the more current method. When you take a look at Pavement ME, you can put in two different types of inputs for material. You can put a fully bound material or an unbound granular material. And that's because Pavement ME was designed looking at asphalt concrete or aggregate base. However, as we discussed, FDR is semi-bound. It It does not behave as a fully bound material. It does not behave as an unbound material. Therefore, we need to kind of look at it as a third type of material. And that is what Dr. Sadie Casillas did toward her master's thesis. Because asphalt, concrete, and aggregate have distinct tests for pavement ME inputs. So what Dr. Casillas did is she took the exact same material, the exact same full depth reclamation, and ran the asphalt concrete test. And that is the schematic on the top. Then she took the exact same material and ran the FDR test, or excuse me, the unbound granular material test. So you have the same FDR material, but she ran two completely different set of tests. One was the test for asphalt concrete, one was the test for unbound granular material. And she found that there was different performance if the input was a bound or an unbound material. So the exact same material, full depth reclamation, exact same design, it performed differently in Pavement ME if you classified it as asphalt concrete or if you classified it as unbound granular material. So I could spend 30 minutes talking about this, and I actually did. If you take a look at the March 7th, 2021 Pavinar, you will see that Dr. Sadie Casillas looked at FDR as a structural design in Pavement ME. So I encourage you to take a look at that Pavinar for the full explanation. Now for construction of FDR, you want to reclaim the existing layers, so you want to make sure you're getting to the proper depth, and because it's partially bound material, you want to make sure you're getting the proper gradation for that bound material as it gets processed in the drum. You may need to add virgin aggregate in order to modify the gradation slightly. That's done during the mix design process, and if it is in fact needed, then you need to place that on the road before you start reclaiming. You add your asphalt emulsion, your cement, and your water. You mix all these materials together. You perform a breakdown compaction, and this is done with the sheep's foot roller. And the sheep's foot roller have those knobs in them, as you can see on the right. You grade and you shape with a grater, and this has established your reclaimed layer. Then you perform an intermediate compaction, and this is done with a pneumatic tire roller, which you can see on the right. It has those individual pneumatic wheels. You shape it with a grater again. You perform your final compaction, which is a steel wheel roller, and you generally do not have it vibrating. You do a final trimming or a tight blading, and then you sweep it. And then your pavement surface, your full depth reclamation pavement surface, can be returned to slow moving, low volume traffic. And that allows it to fully cure. And after about a week, you do another sweep and you apply a surface course, and you have your new pavement structure. It's really a very nice treatment plan, full depth reclamation. So now we're going to move on from FDR to additional resources. So some additional resources that we have, the LRRB stands for Local Road Research Board, and it's a very nice report titled Base Stabilization and Additive Selection for Pavement Design and Rehabilitation. And this is free for download. So if you search LRRB Report 2017 RICO2, so that is an I between the R and the C. I is an Ivan, not a 1. So 2017 RICO2, it was produced in December 2017. We'll talk about the BARM, which is the Basic Asphalt Recycling Manual. This is put out by ARA, the Asphalt Recycling and Reclaiming Association, and FHWA, Federal Highway Administration. And I point you toward the second edition, which can be found by searching FHWA HIF 14001. And this was put out in 2015. And then finally, we'll talk about roadresource.org. Now I'm just going to give a broad overview of these three resources, and if they look interesting, I encourage you to take a look at them to obtain them, because there's a lot of good information in them. So LRRB Report 2017 RICO2. This covers base stabilization and base modification. It looks at in-place pavement recycling materials, and it talks about stabilization, additives, and selections. It also includes steps for successful base stabilization and any sort of stabilization troubleshooting. It includes a laboratory mix design and the associated procedures. It talks a little bit about proprietary products, and it also covers some research on why stabilization works. So this is a very nice comprehensive document, very easy to read. Uh, LLRB always puts out very high quality material, and this is not an exception. And as I mentioned, this is free for download. You simply search the report number above, and remember that is the letter I, RIC, in the report number. The BARM, the Basic Asphalt Recycling Manual, this is a fantastic resource. It talks about cold planning, it talks about hot in place recycling, it talks about cold recycling, which is both cold in place recycling, CIR, and CCPR, cold central plant recycling, and it talks about full depth reclamation. So lots of good resources in here. And it goes deep into the project analysis for each of these treatments, the mix design, the construction, and the specification and inspections. And this can be purchased on the website arra.org. Very good resource, highly recommended. And then finally, this has turned into one of my favorite websites, especially in the classroom, roadresource.org. This is a very nice treatment toolbox. There's 18 treatments and 5 of them directly deal with base and subbase. So if you go to the treatment toolbox on roadresource.org, you can look at FDR, you can look at base stabilization, soil stabilization, lots of good resources there. And for each of these treatments, it includes an overview, pre-construction information, construction information, quality assurance, research and performance, and it has some very nice success stories in the photo gallery as well. So I don't know if you've noticed, a lot of the pictures I've shown in this presentation are from roadresource.org, so you can see there's a lot of nice resources there. In addition, it has 4 calculators. You can calculate equivalent annualized cost, life cycle cost, remaining service life, and cost benefit value of different treatments. And you can explore the impact of using these treatments on a network scale. So here on the right is an example of the life cycle cost calculator. And you can see, well, what's the cost of the putting a chip seal on a road at year 7, putting microsurfacing at year 15, and then performing full depth reclamation at year 25. And you can see for 1,000 square yards, the total life cycle cost is just over $58,000. But you can combine different treatments, you can look at different plans. It's a very nice tool to play with. It also has tabs on pavement preservation, which goes into a lot of what the International Slurry Surfacing Association, or ISA, does. It has a tab on recycling, which goes into what AERA does, and it has a tab on emulsion, which goes into what EMA, the Asphalt Emulsion Manufacturing Association, does. And there are additional resources. And if you are an academic, this is great for the classroom. It can show students the difference between maintenance and rehabilitation. It can show the difference of how changing your maintenance and rehabilitation treatment plans can significantly impact the cost of taking care of a pavement network. I just have a lot of fun with it. So if there's any academics listening in, I encourage you to think about incorporating it into the classroom. So we covered a lot of ground. We covered a background of base and sub-base materials. We covered unbound materials, FDR, and additional resources. So thank you for joining me, and I hope you enjoyed it.